Why do some planets have rings? The sight of Saturn's majestic rings has fascinated us for centuries. Its ethereal, sparkling bands of ice and rock are some of the most iconic images in the universe. But have you ever wondered why some planets have rings while others don't? What makes a planet a ring bearer? And what are these celestial structures made of? In this video, we will explore the science behind planetary rings and answer the question, why do some planets have them and others don't? Quick moment before we begin. Hit like, subscribe, and let's explore the universe together. What are planetary rings? Before we dive into why certain planets have rings, let's take a moment to understand what rings actually are. Planetary rings are collections of dust, ice, rock and gas that orbit around a planet in the shape of a disk. These particles can range in size from microscopic grains to massive chunks of ice and rock the size of houses. In the case of Saturn, the particles are primarily made of water ice, which reflects sunlight and gives its rings that bright, shimmering appearance. The ring systems of other planets, like Jupiter and Neptune, are darker because they are composed of dust and smaller particles. Despite their stunning beauty, rings are not permanent. Over millions of years, the material in the ring slowly falls into the planet or gets scattered across space, so rings are more like temporary features, fleeting cosmic arts. And rings are not exclusive to planets either. In recent years, astronomers have discovered ring systems around smaller bodies too. The asteroid Chariklo was the first such object found to have rings, followed by the dwarf planet Haumea. This discovery shows that even tiny objects in our solar system can host rings under the right conditions. How do rings form? Now, let's get to the heart of the matter. How do these rings form in the first place? The most common way planetary rings are created is through tidal disruption. This happens when a moon or a comet gets too close to a planet within a critical distance known as a Roche limit. This is a point where the planet's gravitational pull becomes stronger than the moon's self-gravity, tearing it apart and creating debris that spreads out into a ring. Take Saturn, for example. Over billions of years, it's likely that several moons have gotten too close to the planet and were destroyed by tidal forces. Their shattered remains formed the iconic rings that we see today. Interestingly, Saturn's rings might not be ancient. They could have formed relatively recently in cosmic terms, and some scientists believe they may only be around 100 years old. But it's not just moons that cause these disruptions. Comets that venture too close to a planet can meet a similar fate, disintegrating into icy debris that forms a ring. However, not all ring systems come from the destruction of moons. Some planets may have material that was never able to coalesce into a moon in the first place. In such cases, the material remains in the planet's orbit, gradually forming rings over the time. Saturn's rings might include some of these materials that were prevented from forming moons due to the planet's strong gravitational influence. Similarly, minor bodies like Chariklo and Haumea may have acquired their rings through collisions or rapid rotation, flinging material into orbit. These rings are narrower and fainter, but prove that ring formation is not limited to giant planets. Why is the Roche limit so important in the formation of rings? The Roche limit is named after the French astronomer Edward Roche, who calculated that a satellite would be torn apart by tidal forces if it ventured too close to a planet. It's not just about distance from the planet, it's also about the size and mass of the planet. Larger planets like Saturn have stronger gravitational forces, so their Roche limits are farther out. When a moon crosses inside this limit, the planet's gravity overwhelms the moon's gravitational self-attraction, causing it to break apart. This debris remains in orbit and over time forms rings. Why do some planets have rings and others don't? Now that we understand how rings form, let's explore why only certain planets have them. The key factors here are gravity, proximity to moons, and the Roche limit. A planet's size and mass play a huge role in determining whether it can support rings. Larger planets like Saturn, Jupiter, and Neptune have stronger gravitational fields, which allows them to create and maintain rings. Additionally, these planets have many moons, which means they have more potential sources for tidal disruptions. Take Jupiter, for example. While Jupiter's rings are faint compared to Saturn's, they still exist. Its strong gravity is capable of keeping smaller, less stable moons in orbit, which can occasionally break apart and form rings. Similarly, Uranus has rings, though they are less visible and more difficult to study than Saturn's. Uranus's rings are likely formed from similar tidal disruption processes. On the other hand, planets like Earth and Mars don't have rings. Their smaller sizes and weaker gravitational forces simply can't support stable rings. And Earth's moon is in a safe orbit far beyond the Roche limit, meaning it won't break up. Interestingly, Mars does not have rings today, but one of its moons, Phobos, might change that in the distant future. Although it's only about 22 kilometers across, Phobos is slowly spiraling inward towards Mars, getting closer by roughly 2 centimeters each year. Right now, it's still too far to form a ring, but scientists believe that in about 30 to 50 million years, Phobos will either crash into the planet or be torn apart by tidal forces before impact. If it breaks apart first, which is likely, the debris could form a temporary ring system around Mars. However, unlike Saturn, Mars has much weaker gravity. That means any rings it gains won't be stable or long-lasting. So even if Mars does get rings, they would disintegrate relatively quickly on cosmic timescales, lasting perhaps only tens of millions of years. Still, for that brief moment in planetary history, Mars could become the only terrestrial planet with rings. The surprise comes when we look beyond the big planets. The discovery of rings around the asteroid Chariklo and the dwarf planet Haumea suggests that even small objects can host rings. This challenges the idea that only large planets can sustain ring systems and expands our understanding of how widespread rings may be in the solar system. Not all rings are the same. While Saturn's rings are by far the most famous, other gas giants have ring systems of their own. These ring systems come in various types depending on the planet and the material in the rings. Saturn's rings, the most complex and stunning. Saturn's rings are divided into several sections, including the A, B, and C rings, each composed of ice particles, dust, and rock. The rings are separated by gaps, like the Cassini division, a dark region between the A and B rings. Jupiter's rings, much fainter and mostly made of dust particles. Jupiter's rings are not as visually striking but still significant for scientists studying planetary ring formation. Neptune's rings. Neptune has a ring system composed mostly of dust and small particles, with a few larger chunks of rock. The rings are faint but still give us clues about how moons and debris interact with a planet's gravity. Uranus's rings. Uranus has narrow, dark rings made mostly of particles that are smaller and darker than those found around Saturn. Their faint nature makes them harder to detect, but they are still an important part of the planet's unique system. Chariklo and Haumea. Chariklo is a central object between Saturn and Uranus, and it was the first asteroid found with rings. Haumea, a dwarf planet in the Kuiper belt, also has a narrow ring. These minor body rings are likely caused by collisions or rotational shedding and are reminders that ring systems are not just for the giants. In conclusion, The rings of planets are not just beautiful decorations in space, they are the remnants of cosmic destruction formed through tidal forces and collisions. The formation of rings depends on factors like a planet's size, the Roche limit, and the presence of moons or debris in the planet's orbit. While planets like Saturn, Jupiter, and Neptune have rings due to their large sizes and strong gravitational forces, planets like Earth and Mars don't, because their smaller masses and farther moons prevent rings from forming. While the rings we see today may not last forever, they are a fascinating snapshot of a planet's dynamic history. As we continue exploring these planetary ring systems, including those around asteroids and dwarf planets, we uncover more about the forces that shape the universe, one stunning ring at a time. Thank you for watching this video. Until next time.